and Ehsan Ghazizadeh, who will talk about TCP congestion avoidance. Please come in front and use the microphone. Good afternoon, distinguished participants. I hope you find it useful and interesting. Thank you very much, Fourier, the previous speaker. He touched on my topic also. Let me talk about the TCP congestion. First of all, let me introduce myself. I'm a network team leader in the second biggest cloud provider in Iran. Been working in the industry for the last 17 years. And in the 10 recent years, I'm mainly focused on SP and DC technologies. I also work as a Cisco and IPv6 trainer. Now we talk about congestion and latency, because when latency happens mainly in congested links, I think, and latency cases. Not because there is too much traffic, not because there is no much control. After 1986, after the first Reno protocol, everyone has implemented TCP Reno protocol. Everyone needs to be Reno friendly. Most network got optimized for TCP Reno. But let me present our view of the problem and our approach. This diagram shows the end-to-end congestion control. As you can see, there are two servers, two edge routers, two receivers. How does each sender know how fast should be the traffic? I mean, what should be the speed for sending traffic? If they send all their traffic, the existing network will be congested, will not be able to deliver all information. So senders implement a congestion control algorithm. It tries to check the available capacity. Let me talk about the history, the Reno and cubic protocols of congestion control. The Reno cubic relies on deep pack and drop packer when buffer overflow, and it keeps the buffer full, and that leads to latency, to losses. And the problem, the real cause is the lack of feedback, insufficient feedback when congestion occurs. And you can see how it works. The packet loss happens due to insufficient feedback. چرا این اتفاق میفته؟ گفتیم مکانیزم سیگنالینگ درستی برای TCP وجود نداره که این اتفاق از این اتفاق بخواد جلوگیری کنه. Now, L4S, the goal of the L4S was to reduce this latency. It's a new standard that Since 2023, there are three different categories that I would like to present to you. The new internet protocol, and there are three types of delays: the propagation delay, limited by speed of light, interface delay, and is addressed by new communication technology standards. But then there are also queuing delays. This is the biggest source of latency variations caused by queuing in network buffers. It can be addressed by avoiding or managing queuing delays. The goal of L4S is to reduce working latency. Like I said, the latency was checked during in a speed test on a commercial PD network. You see the ping grows from 20 milliseconds to over 1 second, and you see lots of packets. So L4S can improve the quality of experience dramatically of any application. So basically L4S it solves the TCP quick scalability problem. It solves buffering and delay problem.
بیاد این مشکل استورج رو حل میکنه و میتونه کاملا یک لیک چند گیگابیت رو با یک اکسپشن TCP پر کنه. مشکل دوم مشکل بافرینگ هست، یعنی میزان بافر اینترفیس هست که بافر ما گفتیم که توی لانچی کاندیشن ولی باعث میشه که ما دراپ داشتیم میزان تاثیری که روی اینترفیس هست افزایش پیدا کنه. اینجا یه حالا خروجی من تحقیق حقیقی گرفتم که نشون میده که شما وقتی میخواید
I've used some data, some metrics demonstrated by Apple. When you watch a video, you see how data is buffered and it eliminates video stalls. Second, L4S solves TCP quick buffering and delay problems, and it can coexist with classic quality of experience and TCP. You see how it works with ECN mechanisms. 2 bits in the IP header. The source declares that the packet should be treated with ECN by setting the IP ECN fields either to 0, 1, or 10. So when congestion happens, instead of dropping the packet, the router sets the IP ECN fields to 11.
دوم که اگر 11 یعنی یک یا 11 سیت بشه به معنی که کانجکشنی در شرایط اتفاق این دو تا کامپیوتر اگر اطلاعاتی رو بفرستن و فرض کنید در اون روتر قرمز رنگ کانجکشن
So
اتفاق
basically,
بیفته
you see two computers that send information into one blue router.
شده فعال شده یا یکی پروسس میکنه به این معنی که
So in time of congestion,
مقصد اون کامپیوتر هست که سمسر اتفاقی که میفته چی هست مقصد وظیفه داره
and what happens
اطلاع بده در شبکه کانجکشن اتفاق افتاده و تو باید دیتاریش رو کانجکشن حالا این چطوری اتفاق میفته توی و توضیح فیدبکی که
the ECN provides feedback
در لایه ترانسپورت اتفاق میفته یا ترانسپورت
and report to the source, and then the source must adjust the rate. Here, whenever we
حالا توی رو در تعداد ست کردن مقصد متوجه که کاندیشن اتفاق افتاده حالا این فرستنده رو متوجه با دیتای با صورت زیادی
so that what happens when the rate of transmission is too high, and then this mechanism is used. Now, next thing is L4S is technology agnostic. Packets are identified by the ECN bits, and it basically offers a uniform rate adaptation mechanism for applications.
اگر همون که یک ست بشه به معنی که کانجکشن خب یک چیزی داره بتونه اکیوریت حالا فیدبک بسیار دقیق‌تری در
we use a concept or notion of more accurate ECN feedback. More accurate notification is fed back in TCP. It's still it's still a draft, but it's very promising. Another quick supported natively via ECN counters. Overall, like I said, L4S combines a new rate adaptation algorithm. It avoids congestion and avoids loss of packets. And it's very simple instrument that can work with any protocols. L4S support is not required on the entire end-to-end path. That is, we need to talk on where you need L4S support. It's not like other protocols or programs that are required on the entire path. You see some of the components where you can use L4S support. Overall, if you plan accordingly, here you see several examples of latency decrease 10 times using the Nokia Wi-Fi beacon. The upper diagram in yellow shows no L4S. with high ping and traffic rate is very low with packet drops. Next line.
This idea again looking common
Now, this was the first world demonstration of L4S running over a fully congested fixed network. And you see on the right the latency CDF zoom and CDF latency.
و کمتر از 1 ثانیه روی شبکه کابل. خب یه مطلبی ما داریم به اسم
Now this next screen is on ECN detection and bleaching. Shows if we lost packets or not. I mean, if data is exchanged, you can tell if the data is kept saved or not. Now there are two different cases. On the right, when bleaching happens, and on the left is no bleaching and destination support. ECN over TCP. So when we send data to other network, so these are the results of the over 300,000 trace routes. The rates of bleached results in different regions of the world. Now, concluding, ECN bleaching is still around. And where the bleaching is happening, we can use Pietrasanta trace route to help to identify. And the truth is you cannot fix what is not visible.